All right, in this section, we're going to be talking about continuity. So the idea of continuity is pretty simple. So for a function to be continuous, it has to be unbroken, which basically means there are no holes or jumps or gaps, no asymptotes, anything like that. So the easy way to think about if a function is continuous is if you can draw the entire function without picking up a pencil. So here are three examples of functions that are not continuous. So this first one, f of c is not defined. So we have a hole right here. That would be a discontinuity. Second type is if a limit doesn't exist. In this case, the limit doesn't exist because the left and the right don't meet up. So that would be a discontinuity. Third kind is if the limit doesn't actually equal the function value. So in this case, the limit does exist, but the actual function value at c is not the same thing as the limit. It's up here. So that would be another type of discontinuity. So all three of these, you wouldn't be able to draw those with one smooth line with your pencil. You would have to pick it up. So that's how we know those are not continuous. So that's just the idea. So the actual definition of continuity is right here. So a function is continuous at a point C if the following three conditions are met. So first of all, the function has to actually be defined at C, which basically just means you can't have a hole, you can't have an asymptote, nothing like that. Second condition is the limit has to exist, which also sort of makes sense if you think about it. And then the last part and the most important part is that 1 and 2 need to equal each other. So the limit has to actually equal the function value. So if all three of these conditions are met at a point, then that means the function is continuous at that point. So continuity on an open interval. So a function is continuous on an interval if it's continuous everywhere in the interval. Kind of makes sense. A function that's continuous on the entire real line, which just means from negative infinity to infinity, we call that everywhere continuous. So some examples of functions that are everywhere continuous would be just regular polynomials or sine or cosine, an exponential function, anything that you know doesn't have a hole or a jump or an asymptote. All right, functions where you kind of need to be careful are rational functions, piecewise functions, tangent, secant, cosecant, things like that that you know might have a hole or an asymptote. All right, so examples. So this first one, we have f of x equals 1 over x. So just looking at that, you should already know that when x equals 0, you're going to run into an issue. We would get 1 over 0, which we know is an asymptote. So this function is continuous everywhere except x equals 0 because there's an asymptote at x equals 0. Which really just means the limit is it doesn't exist because it's unbounded. Number 2, so this is a piecewise function. So piecewise functions, we do need to be careful to check that they're continuous because this one actually is continuous. Because in this particular case, the limit does exist. They're both approaching 1 actually as x gets closer and closer to 0. And the function value is actually 1. So you could draw this without picking your pencil up. So this is everywhere continuous. Number 3, we've got a rational function. This one, there is a hole at x equals 1 because if you were to plug in x equals 1, you would get 0 over 0, which we know is a hole. So this is continuous everywhere except x equals 1. Right, so if a function is not continuous, then we call it discontinuous. You probably could have figured that out. Discontinuities, there are 2 types of them, removable and non-removable. Removable discontinuities could be made continuous by defining the function so that the function is continuous. So that's kind of a weird definition, but let's look at the examples here. So these are 2 examples of non-removable functions. There's no way that you can define if we said that this x value was c right here, there's no way you could define that to make this continuous. Same thing with this. It is kind of a bad drawing, but this is an asymptote. So there's no way you could define the function at x equals 0 to make that continuous. This one, however, this is just a hole, so the limit exists, which means you could actually define the function right here at this x value. You could kind of fill that hole in to make this continuous. So that's what makes that a removable discontinuity.